7.1 goes over trig identities. You want to think about these like equations, or they are going to be given to you as equations, but you want to realize that an equation is two statements that are equal to one another. These identities are working in the same way. So an identity is an equation that is true for all values of the variables. The last two equations that you see here, the x plus 1 squared is equal to x squared plus 2x plus 1, and the sine squared t plus cosine squared t is equal to 1, are identities. But the first one that you see, that x plus 2 is equal to 5, is not, since it's not true for the values of x other than 3. So, with these trigonometric identities, you're going to be working specifically on two types of identities. The first is the reciprocal identity, which just tells us that cosecant of x, cosecant of theta, whatever, of anything, is 1 over sine x, sine theta, sine whatever. The secant of x is equal to 1 over cosine of x. The cotangent of x is equal to 1 over the tangent of x. Tangent x is equal to sine x over cosine x, and cotangent x is equal to cosine x over sine x. Again, these are reciprocal identities. The second trigonometric identity that we're going to be working with is the Pythagorean identities. This just tells us that if we have sine squared x plus cosine squared x is equal to 1, that's an identity. We also could use tangent squared x plus 1 is equal to secant squared x, and 1 plus cotangent squared x is equal to cosecant squared x. These can be interchanged, so like, for example, the sine squared x plus cosine squared x is equal to 1. You can move that cosine squared x over to the other side of your equal sign, and it would give you sine squared x is equal to 1 minus cosine squared x, and it means the same exact thing. So with these, it is in your best interest to take a screenshot of these two identities, because we are going to be working with them over and over again throughout this entire lesson, and import them into wherever any of these problems occur, so that way you have your identities there and you can refer to them. If we look at simplifying trig identities, it tells us that identities enable us to write the same expression in different ways. It's often possible to rewrite a complicated looking expression as a much simpler one. To simplify algebraic expressions, we use factoring, common denominators, and your special product formulas. To simplify these trigonometric expressions, we can use the same techniques together with the fundamental trigonometric identities. So those identities that we just went over, those two types, we will be using with our different operations. If we look at example 1, it tells us to simplify the expression cosine t plus tangent t times sine t. Your whole idea with these, you want to focus on turning anything that's not cosine or sine into cosine or sine. It's going to be a lot easier to work with sine and cosine than it would with any other type of trigonometric function. So if we look here, we have cosine t. It's the same thing as saying cosine x or cosine theta. Cosine t, we don't really change that. However, your tangent t, we can change by using the tangent t is equal to sine t over cosine t. When we do this, I'm going to leave everything else the same, but just change out this tangent t. So this is going to leave us with cosine t plus, I'm changing out that tangent t to be sine t over cosine t, and we multiply this by sine t over 1. Now from here we can multiply that sine t over cosine t times sine t over 1 multiplies, and we just are left with cosine t plus sine squared t over cosine t. Now, in order to add these two fractions, we can put that cosine t over 1 and then find our least common denominator. Our least common denominator is that cosine t, so we would multiply the top and the bottom of this first fraction by cosine t. This leaves us with cosine squared t plus sine squared t all over cosine t. From here, look at your Pythagorean identities. Cosine squared t plus sine squared t. Cosine squared x plus sine squared x, what is it equal to? It's equal to 1. So change that out. This whole thing here is equal to 1. So this is giving us 1 over cosine t. This is your answer. This is the simplest form of this expression that's given to you of cosine t plus tangent t times sine t. The next part that we're going to be looking at is proving these trigonometric identities. It tells you that many identities follow the fundamental identities. In the examples that we're going to be doing, we learn how to prove that a given trigonometric equation is an identity, and in the process, we see how to discover new identities. It's easy to decide when a given equation is not an identity. What we also need to do is to show that the equation does not hold for some value of the variable. So, steps in doing this. First thing that you're going to do is you're going to start with one side. Pick a side. Doesn't matter which one. Normally, you want to work with that harder looking side. Your goal is to transform it into the other side. Again, it's usually easier to start with the more complicated side. Use your known identities. You can use algebra and the identities to change the side that you started with. Bring fractional expressions to a common denominator, factor, use fundamental identities to simplify them. Convert to sine and cosine. If you are stuck, you can find a helpful way to rewrite these by turning them into sine and cosine. It'll make your life a lot easier. If we look at example 3, it tells us to consider the equation cosine x times cosine theta times secant theta minus cosine theta is equal to sine squared theta. The harder of these two sides is going to be the left side. You have more trig identities there. You have more trigonometric functions there. So work with the left side first. What I like to do when I work with these is I like to draw a line right down the middle. That tells me or helps me to separate the two sides. So the first side I'm going to work with is this cosine theta times secant theta minus cosine theta. I'm not even going to worry about or work with that right side yet. If I want to just put down that sine squared theta to help me remember that's what's on that side, that's fine. You can do that. Look at your identities. You have cosine, you have secant, you have cosine. Cosine and cosine, they're already in terms of sine and cosine. So try to move that secant of theta into cosine or sine somehow. If you look at your identities, that secant x is equal to 1 over cosine x. So we can turn that secant theta into 1 over cosine theta. So we're just going to rewrite this as cosine theta times 1 over cosine theta minus cosine theta. You realize that I put this cosine theta up a little bit so that way I can turn it into a fraction that's over 1, and I can go into solving this or simplifying this by combining my fractions. In order to combine fractions, you need like denominators. So that cosine theta over 1 has to be multiplied top and bottom by cosine theta to give us the like denominator that we're looking for. So this becomes cosine theta times 1 minus cosine squared theta all over cosine theta. Now you could look at this and say, in front of my fraction, I have the same exact term as what's in my denominator of my fraction. So if I was to simplify before I multiply, they would cancel each other out. So the only thing I'm left with is 1 minus cosine squared theta. Now looking at your identities, involves a cosine and a 1, or sorry, a cosine squared and a 1. If we look at this, sine squared x plus cosine squared x is equal to 1. I can move that cosine squared x over by subtracting it from each side, and it leaves me with sine squared x is equal to 1 minus cosine squared x. So look at that. We have the same exact thing here. So that 1 minus cosine squared theta is equal to sine squared theta. This is in its simplest form. From here, look back at the original equation that you had. You have cosine theta times secant theta minus cosine theta is equal to sine squared theta. What was your right-hand side of that equation? Sine squared theta. Are these two sides equal to one another now? They are. So this is a trigonometric identity. For example 5, we're told to verify the identity of cosine u over 1 minus sine u is equal to secant u plus tangent u. Now, if I look at this, my left-hand side is already in terms of sine and cosine. My right-hand side is not. So I'm going to work with that right-hand side first before I do anything else. So working with that secant u plus tangent u. So I have secant u plus tangent u. I want to try to put these in form of cosine or sine. Secant, I see that is the 1 over cosine x. So I'm just going to change this into be 1 over cosine u. That tangent u, we see that tangent x is sine over cosine x. So this is going to turn into sine u over cosine u. Simplify these two fractions. We have like denominators, so just add straight across. We have 1 plus sine u over cosine u. From here, this is still equal to what you had on the other side of that equation. So it's still equal to cosine u over 1 minus sine u. I don't like working with fractions. So if I don't want to work with fractions, I'm going to cross multiply with this and work with specific terms that are not involved with fractions. So if I multiply the cosine u times cosine u, and I'm going to multiply 1 minus sine u times 1 plus sine u. Cosine u times cosine u, that's giving us cosine squared u. 1 minus sine u times 1 plus sine u, difference of squares, that's 1 minus sine squared u. Look at what you have. You have a cosine squared, you have a sine squared, you have a 1. What Pythagorean identity works with sine squared and cosine squared? It's the sine squared x plus cosine squared x is equal to 1. If you moved that sine squared u over to the other side by adding it to both sides, This leaves us with sine squared u plus cosine squared u is equal to 1. This entire equation is the same exact thing as your Pythagorean identity, sine squared x plus cosine squared x is equal to 1. If we look at our next example, we're given 1 over cosine theta is equal to tangent squared theta over secant theta minus 1. That 1 plus cosine theta over cosine theta, it's already in terms of sine or cosine, so don't work with it. Work with the side that's that tangent squared theta over secant theta minus 1. The tangent squared theta. You have a tangent squared x in your Pythagorean identities. However, I'm going to leave that one alone and look at that secant theta. That secant theta, okay, hold on. Never mind. So your secant theta minus 1, we are going to look at by using that trig identity with the tangent squared x plus 1 is equal to secant squared x. The reason why is because if we rearrange, we're going to look at just our Pythagorean identities right now. If we rearrange this and subtract the 1 from each side here, we have tangent squared, I'm going to use theta so that way it's the same way that you would see it in your equation that is given to you, is equal to secant squared theta minus 1. Now that secant squared theta minus 1 is not the same as secant theta minus 1. However, it is a difference of squares. So we can factor it into tangent squared theta is equal to secant theta minus 1 times secant theta plus 1. So now you see that, yes, you have something that is included in the original equation that was given to you, which is that secant theta minus 1. What's happening to that secant theta minus 1? It's being multiplied by the secant theta plus 1. So divide each side of this by secant theta plus 1. These cancel, so you have secant theta minus 1 is equal to tangent squared theta over secant theta plus 1. That's what you were looking for. This is the same thing as what you have in the denominator here. So change it out. Rewrite it. This is going to give us tangent squared theta all over your fraction of tangent squared theta over secant theta plus 1. Fractions mean division. So this long line just means divide the two. When you divide fractions, remember you keep, change, flip. So this is tangent squared theta over 1 divided by tangent squared theta over secant theta plus 1. If you keep, change, flip, this gives us tangent squared theta over 1 times secant theta plus 1 over tangent squared theta. Those tangent squared thetas would cancel, and you just have secant theta plus 1. From here, secant is equal to what? Secant theta. Look at your basic identities. Secant x is equal to 1 over cosine x. So change it into cosine. This is going to give us 1 over cosine theta plus 1. You need like denominators in order to combine your fractions. This 1, which is really 1 over 1, gets multiplied top and bottom by cosine theta. So we're going to rewrite this as 1 plus cosine theta all over cosine theta. Look at what you started with. It is the same exact thing. They are equal to one another. So this is an identity. For our last example for this lesson, we're told to substitute sine theta for x in the expression the square root of 1 minus x squared and simplify. If I rewrite this, I'm going to have the square root of 1 minus, we're writing in sine for x, sine theta squared. This is going to give us the square root of 1 minus sine squared theta. This 1 minus sine squared theta, guess what? You have a sine squared x in one of those Pythagorean identities, which is that sine squared x plus cosine squared x plus 1. So rearrange those terms to make it easier for you to deal with. You're looking for 1 minus sine squared theta, I'm sorry. So if we subtract this sine squared x from each side, you're going to have cosine squared x is equal to 1 minus sine squared x. So that's the same exact thing that's in that radical. So this is the same exact thing as saying take the square root of cosine squared x. Well, the cosine squared x is just cosine x. Or here, this is theta, I'm sorry. This is theta, cosine theta, cosine theta.